Alright, welcome to Physics 224 Day 3. So we were talking about the end of last time some ideas about electric field, how electric field is related to force. So we had electric field is force per unit charge, or we could say that if we wanted to get the force, then we just take the charge times the strength of the field at whatever point we happen to be at. And so I think I put up the equation that the electric field then is, just looking at the force equation, was Q over R squared, but now we're dividing by Q, so the electric field then is just KQ over R squared, and then we have the R hat, the direction vector, which we usually get by drawing a picture and figuring it out, and the force and the field go in the same direction. All right, so when we talked about if we had a point charge, if it's positive, then the field lines all point away. But if it's negative, then they would all point in, because it's the direction that a charge would feel. So if we put a positive charge would feel. So if we put a positive charge next to a positive charge, it gets pushed away. If we put a positive charge next to a negative charge, it gets sucked in, right? And so that will help you decide which direction the lines go. Hopefully it makes a lot of sense that way. So let's do an example. Let's just say we have two negative charges here. Let's say they're separated by, what did I say? For an example, 0.1 meters, so 10 centimeters. And then let's give them some numbers here. 20 microcoulombs for this guy and 30 microcoulombs for this one. Alrighty, so if we're looking at this and we're going to put a positive test charge, and this is all in a nice line, so we don't have to do x and y components, we'll just have everything be x. And so let's just say if we were putting our test charge right here, what would happen? What is the field like over here from these 2 point charges? So remember, superposition says we can figure out what the field is like from this one, what the field is from that one, and add them together, right? So we can do this one separately as if these were the only 2 things here. Same thing here. We could do it with any number of charges, just add them all up separately. So if we're going to take this point, we'll call this one charge 1 and this one charge 2. And so let's make this one blue and this one pink. And so for E1, what would the field E1 be over here? So positive test charge is going to, from a negative, this is I guess I should put some negative signs on these guys, since that's how we decide. So these are Q's, Q2, this is Q1. All right, so E1 then, the field from charge 1, what it causes at this point would be attractive towards point 1, right? Because positive charge would be pulled towards a negative charge. So E1 might be something like this over here, right? And then what would E2 be? Well, E2 is also a negative charge, and it's pulling over there. It's bigger in size, but then it's farther away. Remember, the farther away is squared, and so the effect is small. So E2 maybe be something like this, because this point is quite a bit farther away from 2 than it is from 1. All right, but they're agreeing with each other, saying the positive charge should come this way, right? Same kind of thing out here. If we do this one, point out here, let's do E2 first. E2 is pointing this way, right, towards it. E1 now is far away, so E1 would be a smaller pull. Or these are fields, so this is just the stronger point in that direction. It says we go there. So to figure out what the force would actually be, we decide we have to know what size of charge we're putting in here, multiply the field by the size of the charge, and that would tell us the force, the strength of the pull. But this is just giving us a relative map, a map of the relative size of what a force would, what a charge would feel, what kind of force it would feel. So this is the electric field vectors telling us that information. Okay, how about in the middle? So if we pick a point, so this one is smaller, this one is bigger, and so if we're kind of trying to pick a point where it's kind of close to 0, we would have to put it closer to the smaller one. but it's by a square. Anyway, I'm not going to do the details, but let's just pick a point here. Let's say it's 0.3 meters from the 0.03 meters from the smaller one, just to give it more of a fighting chance, right? And so, because what's going to happen in here, if we put a point charge in here, a positive test charge, they're both going to want it, right? They're both going to be, it's going to be attracted to both of them. E1 is going to be this way, or E1 says the charge should go that way, and E2 is going to say the charge should go this way. Right? So these again are fields, but they're directly related to force just by the size of the charge, and so you can get the directions by what the force would be. So somewhere in the middle here, since they were fighting each other in the middle, somewhere in the middle we would expect there to be a point where it could actually just kind of balance there. They're both pulling the same amount, a balanced tug of war, and it would be stuck in the middle and just not moving, right? First of all, let's just go ahead and calculate the total field at this point and see how close we got. Sorry about the volume there. Let's mute my computer so it doesn't make noise. Okay, so let's go ahead and calculate. So if we want E total, so E total, I'm guessing it's probably still going this way. I wanted to make that a different color. All right, so E total is going to be E1 by superposition, E1 plus E2, right? All right, so we can calculate the E, each separate E, and then add them together. And this is nice because they're all just in the, say, X direction. We don't have to worry so much about the vectors because they're all lining up with each other. All right, so let's get E1. That's probably good to go ahead and keep them as vectors as a practice, just to keep track of it, but we know they're all lined up. So E1 is going to be K Q1 over R1 squared times R1 hat, basically making it all kind of generic form. K is the Coulomb constant, 8.99, 10 to the positive 9. Newton meters squared per Coulomb squared. Q1 I said was, and we're going to take care of the directions without the sign, so we're just going to use positive 20, 10 to the negative 6 coulombs here, and R squared is the distance. R is the distance here. We said that was 0.03 meters. It's going to be squared, and the direction, let's just do it for practice, negative I hat, right? Because it's in the negative X direction. I think if I hat is east, it's the negative east direction, so it's west. But anyway, negative I hat is the vector we would put on there. Alrighty, so let's plug those numbers in. 8.99E9 times 20E negative 6 divided by 0.03 squared. Okay, that is awfully big. But coulombs are small things, so I guess that works. E1 is basically 200 times 10 to the 6th I hat. And what are the units of electric field? It's force over charge, so it's newtons per coulomb. Right, but 1 coulomb is a huge thing, so that's why the newtons per coulomb are so huge. Alright, so that's E1. I lost my negative sign somewhere, but we found it, put it back there, going that way. Alright, E2. Same formula in general, KQ2 R2 hat over R2 squared. 8.99 10 to the 9th, same units on everything here. This one though is 30 microcoulombs, 30 10 to the negative 6, and then dividing by, if this distance is 0.3, this distance must be 0.07, right, because the whole thing was 0.1. Meters, coulombs, this one is in standard units, that's good. What is its R hat for this, for number 2? This is a 2. It's going straight to the right, straight east, straight positive x, so we would just have I hat. Okay, and so plugging in the numbers, looks like, we'll call it 54. 54 times 10 to the 6th newtons per coulomb I hat direction. Alright, so then E total is going to be E1 plus E2, like we have up here, going to be negative 200 I hat plus 54 I hat, all these times 10 to the 6th newtons per coulomb, so meganewtons per coulomb if you want to say it that way. And so we end up with what, 200 minus 54, negative, anyway, I could do it in my head but I don't feel it. 146. 146, we can, wherever we want to put the 10 to the 6th, I hat newtons per coulomb. That is E total. Alrighty, so I was right in my guess that it is going in the positive x direction. There's no negative sign here. Oops, I was wrong. Anyway, sorry, I was wrong. It's going the other way because we have negative 200, positive 54, so it's a little too close to that guy. Yep, so to make it be more balanced, we would need to go further than 0.03 away from the first charge. So let's just do that. So let's calculate. Let's redraw our picture. Um, 20. And let's figure out some point here. Let's just call it x. Some point x where the fields do equal 0. Okay? So we want to know at this point x, E total is 0. Okay? What is x? Alright, very good problem. So we kind of got the same work, same setup, same kind of ideas here. So E total is still going to be E1 plus E2, right? E1 is going to be same kind of thing, K Q1 over R1 squared, R1 hat, all that kind of stuff. So we've got same K. You want to put in a number, how much numbers to put in, I don't know. Well, let's just do K, and then we've got 20 microcoulombs, and then R hat for E1, still pulling back, so it's negative I hat, and R1 itself is X, right? So we're going to have X squared. Good. For E2, this is 1, and this is 2. So for E2, again, KQ2 over R2 squared, R2 hat. So it's going to be K, 30 microcoulombs. Its direction is positive X, so just an I hat. And divided by its distance is the 0.1 minus X, right? 0.1 minus X to get the leftover distance. The whole thing is 0.1, this much is X, so this is 0.1 minus X. Right? And don't forget to square it there. Alright. So, if we want E total to be 0, right? This is E1 plus E2. So that tells us E1 has to be negative E2, right? To get those to be 0. Or magnitude-wise, magnitude of E1 has to be magnitude of E2. Alright, so looking at these two numbers here that we've found, E1 and E2, we kind of forget the unit vectors. We just say that K 20 microcoulombs over x squared has to be equal to K 30 microcoulombs over its R, which is 0.1 minus x squared. Alright, so that's saying the magnitude of E1 and magnitude of E2 have to be equal to each other. So some things can cancel. The k's, divide both sides by k, or multiply by 1 over k on each side. So the k's are gone. Divide through by microcoulombs, 10 to the negative 6. On both sides, the micros go away. And so, I don't know how you like to do your algebra. So we'll end up with 30 over x, oh, it's not 30, that's a 20. 20 over x squared equals 30 over 0.1 minus x squared. You can either think of it as cross multiplying, or however you want to, or multiply both sides by x squared and both sides by this. We can think of it as cross multiplying, maybe is the easiest way to think of it. So you get 30x squared. Multiplying, one way is just think multiplying both sides by x squared. So the x squared goes up here, this x canceled out, and then multiply both sides by this one. 30x squared equals 20 times 0.1 minus x squared. All right, however you like to do your algebra. It might be good to let's just divide both sides by 30 also. So we're going to get x squared equals 2/3 0.1 minus x squared. Just dividing through by 30 and noticing that there's a 10 that can cancel. Let's take the square root of both sides. Right, because we got squared and squared. We could multiply this all out and do that, but let's take square root of both sides, and we'll just take, we want x to be positive, so we're going to ignore the negative answer. So we take the square root of both sides, we get x equals the square root of 2 over the square root of 3 times the square root of 0.1 minus x squared. So just the 0.1 minus x, right? Square root of everything. And so x, multiply this out. Maybe let's leave it as just the square root of 2 over 3 might be easier to deal with. So this is equal to the square root of 2 over 3 times 0.1 minus the square root of 2 over 3 times x. Just distributive law there. And so let's bring this add plus square root of 2 over 3 to both sides, square root of 2 over 3x to both sides. And so we end up with x plus square root of 2 over 3x equals square root of 2 over 3 times 0.1. And so factor out an x, 1 plus square root of 2 over 3 equals square root of 2 over 3 times 0.1. So x equals, running out of room, hopefully it's not off the screen, square root of 2 over 3 times 0.1. That's the top, and divide through by this. 1 plus square root of 2 over 3. However you like to do your algebra, do your algebra. So let's plug that in, and so we'll have the square root 2 divided by 3. That whole thing, this is divided by, don't forget my divide sign there, divided by, open some parentheses, 1 plus, again, square root of 2 divided by 3. Alright, calculator is nice, but it says square root of 6 minus 2. Let's get a number. So about let's see. What have I done? Okay. 0.449, so let's just say 0.45. No. I lost something. I forgot to multiply by 0.1. Okay, no. Says it has to be less than 0.1. Let's do this again. Let's go get that thing. Where to go? Fix this equation. Let's do 0.1 times, don't forget the 0.1 times square root of 3 or square root of 2 over 3. Yes. So I guess, yeah, just multiply your answer by 0.1. Yes, that makes more sense. 0.045 meters. Okay, so the x place, we did at 0.3 and we knew that was too close to this guy, so 0.045 meters from charge 1 is where the field goes to 0 in between the two charges. All right, so a little bit of algebra, but a little bit of, hopefully a lot of practice thinking about the E fields, how you build them, these unit vector ideas, superposition, add the two together to get the total. While we're here, let me take a step back. And so if we go back to this part of the problem where we calculated the field at 0.03 meters right there, what would be the force here? Well, we need to know the charge to know the force here. So that would say, let's say we're going to put an electron there. We put an electron at 0.3 meters in between, 0.03 meters in between. What is the force the electron is going to feel? Well, force is Q times E. What's the charge of an electron? It's 1 E, right? But what is 1 E in coulombs? 1.602, 10 to the negative 19 coulombs, times our E field, negative 146, 10 to the 6th, I hat, whatever, it's in the, it's pointing in the negative x direction, but then the charge, actually I should put a negative on here. However you want to keep track. You want to keep track of it as negatives and doing it math-wise to figure it out, or if you want to just remember, if we have, so this ended up being wrong, so E total is going that way. All right, so if a positive charge gets pushed to the left, then the negative charge is going to get pushed to the right. So in either way, this force for my electron should be going in the positive I direction. So if I had negative on my charge, my negative on my field, negative times negative makes a positive, or just thinking of it by looking at the picture, either way you like to do it, it's fine with me. Numbers wise, 1.602 times 10 to the negative 19. I typed that wrong. Times my field, 146, positive 6. We end up with a force of 23 times 10 to the negative 12 newtons. Very tiny force on a very tiny electron, right? But anyway, hopefully you get the idea. Fields and forces, very closely related. Just pick a charge. So I could get the charge on a proton, just put a plus here, right? Or if I had some sort of atom that has a net positive 2 charge, I would multiply it by, get the charge of 2 times an electron and multiply that times the field. Whatever charge we have, now that we know the field at that point, whatever size charge we have, we can calculate its force just by multiplying charge times the field. So that's a benefit of having the field. Okay. Let's look at another example. So let's take a dipole. So a dipole, di means two poles. Dipoles are just, usually it's like an atom that's stuck together and has, maybe like a water is a dipole molecule, it has a positive end and a negative end. But let's just say we're going to take them as point charges. And so let's just do an example here where we have 5 let's do nanocoulombs and negative 5 nanocoulombs. So we have a dipole equal charges, so it's balanced overall, balanced molecule, balanced whatever it is, and but the equal and opposite charges. And so what kind of field, if we want to kind of call this our x and y axis, what kind of field would we have up here? Some distance y above the field. Let's just pick a number. I don't know. Let's just say 8 centimeters. So this is going to be our point where we want to know what is the electric field here. To start with anyway. Okay? So, get some colors going again just so we can kind of see, and probably should have made things bigger, but whenever we're doing electric field, we always think of a positive test charge. And so if we put a positive charge right here, what kind of force direction do we have from this guy? So how do we figure that out? Well, we make a line directly connecting, because the force can only act in the line directly connecting. And if it's a positive charge, test charge, to a negative charge, they like each other, right? So we're going to get some sort of a force in that direction, but we're not calculating force right now, we're calculating fields, so we call this E, I guess we'll call this 2 and 1, E2. Okay? But the other end of the molecule, these two are connected, the other end of the molecule is positive, right? And so it's going to push away a positive charge. It's the same size, but it's closer. Oh boy, I might not have given myself enough room. Anyway, E1 will be something like this, right? The resultant, remember when we add vectors, and really let me make E2 a little shorter, because E2 is further away, so it should be shorter. Sorry, messy work here, but let's make E2 a little bit shorter. So E2 is really only this long. Let's go with that. And so to do pictorially calculate where the answer is, we can make a parallelogram out of the two sides, and then our E total would be the diagonal of the parallelogram. So E total would be those two, or that vector as the diagonal of the parallelogram. E total, so this is the whole answer, E1 plus E2. Remember, superposition says do one at a time, add them together. Okay, and so let's figure this out. So E1, and what is E? How do you find E? K, Q over R squared times the direction vector. Right? And so I guess put ones on everything to keep track of, except for the K, keep track of what we're doing here. So E1, in this case E1 is right underneath, so that's going to be nice. K, same old K, 8.9910 to the 9th. Some problems might tell you to do it in terms of epsilon naught. Remember, K is 1 over 4 pi epsilon naught. Where'd my 4 go? And so if it asks for that, you can just directly substitute in. But K is kind of nice, just a few less things to keep track of in the equation. All right, Q1. Q1 is 5 nanocoulombs. What is nano? Nano negative 9. All the n's. Nano negative 9. So 5 10 to the negative 9 coulombs. And what is R in this case? Again, it's nice and straight. 8 centimeters, 0.08 meters squared. And how about the R hat? Well, we drew it. The field is pointing straight up. Straight up is like north, which is like a J hat. The y direction, positive y direction, J hat vector. Okay, so that tells us the direction for E1. Plugging in numbers. We get 7.0. I don't know, keep 3 this time. 3 is what I asked you to keep on the test. Let's do that for practice. 7.02 times 10 to the third. Again, what was the field? It's the force per charge, Newton per Coulomb. And let's not forget our J hat. We're telling us it straight up. Okay, E2. Same kind of thing. KQ2, R2 hat over R2 squared. A little more complicated though because we got angles in here. Did I say how far apart these were? No, I didn't. They'd be very small compared to what if it was a real molecule, but let's just do some sort of made up other things, not a molecule. Let's just say this is, what should we say? 0.2 centimeters apart. All right, so 0.2 centimeters would be 0.002 meters, right? 2 millimeters apart. Alrighty, so not drawn to scale, by any means drawn to scale. Okay. So, K. K is easy. 8.99, 10 to the 9th. Right? Newton, Coulomb square, all those units on there. Q2, easy still. 5 nanocoulombs, 5, 10 to the negative 9th in terms of size. Unit vector is going to be out here. Divided by, okay, what is this distance? So, it's going to be really close to 0.08, but let's go ahead and calculate it for real. All right, so we've got a little triangle. We want the hypotenuse of the triangle, so it's going to be a squared plus b squared equals c squared, right? So c squared is what we want on the bottom, actually. R2 squared, so it's going to be a squared plus b squared. So a is 0.08 and b is 0.002 squared, right? So r is the square root of that, but then we're squaring it, so we get back to just 0.08 squared plus 0.002 squared. All right, well, that's not so bad. And then, what's the direction? All right, so we need our little unit vector, 1 unit long, pointing in this direction. It's going to have a positive I hat coefficient, positive x direction, but it's negative y, so it's going to have a negative j. So we can just put our I hat and j hat here and put a negative over here, so we remember to put a negative on our j hat. One thing to notice in Achieve and in books, quite often they don't put hats on these I and j, so they just make them a bold looking thing, and that'll be the vector. So just kind of watch the notation there. All right, so, but what are the ratios here? So we don't really have an angle. I just gave you sizes, so we want to go ahead and do on our equation sheet, we have the ratio, the ratio method, the similar triangles method. Anyway, we're going to put Rx, which the x component here is 0.002 on the top, and divide by that whole thing. Let's just say, call it magnitude of r for a minute. All right, and then the y part is the y part of the triangle, which is 0.08, and then divided by this magnitude of r. All right. So in class we did it all just in centimeters, or we could do it in millimeters, or we can do it in meters. For this, it's just a ratio, but since we already converted things to meters, let's just keep it there. So let's figure out what is magnitude of r in meters. Like I was just saying, it's the hypotenuse of the triangle, so it's 0.08 squared plus 0.002 squared, square root of that, to get just the magnitude of r. So let's do that. Square root 0.08 squared plus 0.002 squared. So we get I didn't pick very good numbers, but anyway, 0.08002. So very, very close to just being 0.08. Well, let's just go with it. Rounding, it is 0.08. So technically, let's put it technically it doesn't matter rounding errors wise. It comes out to be very close to this length because it's just the scale of things, but we'll go with it. All right, so calculate this number, 8.99 E9 times 5E9 divided by, we'll need some parentheses here, 0.08 squared plus 0.002 squared. Okay. No, I messed something up. Anyway, let's try that again. 8.99 exponent 9 times 5 exponent negative 9. I think I forgot my negative 9. Divided by, in parentheses, 0.08 squared plus 0.002 squared. That looks better. So we get 7.0. Let's keep an extra sig dig as we're doing these calculations in the middle of the calculations, times 10 to the third. And then we've got 0.002 divided by 0.080. So 0.025 I hat minus 0.08 divided by 0.08. Okay, so 1 J hat. Okay, and this is still newtons per coulomb. Okay, so we can multiply this out. 7.019 exponent 3 times 0.025. 175 I hat minus 7.019 10 to the third J hat. That's per coulomb, that's E2. Alright, we're getting there. So now we want E total. E1 plus E2. Don't forget the hats. Alright, so E1 is, if we want to just get rid of the exponential notation, 7,020 J hat, and then that's E1, and then E2 is 175 I hat minus 7,019 J hat. Okay. Alright, and that's probably just all a rounding error. Yeah. And so we end up with basically 175 I hat is E total. Alright, so even if this had been, if I had made it further apart, we would still end up with the X component canceling? Is that right? No. No. It wouldn't. It's just because of that. If we kept it as 1 plus 1 J hat, realizing that we are kind of violating some significant figures information, let's just do that just for the math, keeping track of the math. Then if we wanted the magnitude of E total, what would we do? Well, we've got X and Y components, so it'd be the square root of EX. This would be like EX, and this is EY. So the magnitude of E total would be the square root of 175 squared plus 1 squared. Alright, and so I don't know if that's going to have any significance either. 175 squared plus 1 squared, square root of 176. Yeah, so it still ends up being 175.003, so basically 175. So kind of bad problem for significant figures, but if for the process wise, if you had something significant, you have to square both, add them together. Again, it's just the components of the triangle kind of idea to get E total. All right, so let's think about a little bit different aspect for what if we had something that was, say, right here in the middle, in between these two. Right? What kind of field would we get here? Well, if we think about the parts, let's think about the directions first. So still E1 is going down, E2 is going away. Alright, still don't like each other, but this one now is at an angle. So we got both of them at angles. Alright? And what ends up happening is, if we make our parallelogram here, our new E total looks like it goes straight to the side, right? So is that true? Is this much up the same as this much down? Do they cancel each other out? How could we prove that? Well, we would have to know the angles here, but by symmetry, we can say by symmetry they do cancel out, all right? So if we have equal angles, we have equal distance, we'll have equal angles here, if we have equal distance, these distances will be equal, so the forces will be the same size, and so the cosine of this angle, which is the same, right, this E2x is going to be E2 sine theta, and y, we're going up and down, is going to be E2 sine theta, yes, if this is theta. And then this one's down is going to be E1. I'm mixing my ones and twos. Anyway, it's the same equation, but this one's down. This is from E2. This is E2. This is E1. And so, but basically same argument. They're going to be equal and opposite, and so this one is going to be E1 sine theta. And since we're making it nice and symmetrical, the thetas are the same, and so let's see which one's the negative one. E2 is a negative one because it's going down, right? And so what I'm saying, do these cancel? It looks like these would cancel out, and I'm arguing that they do cancel out. For one, the thetas are the same, so the sine thetas are equal. So now are the E1 and E2, the magnitudes of them, equal? Well, they're just KQ over R squared, right, both of them. And the Q's are the same. They always were the same magnitude-wise. K is, of course, the same K. Now we've made these R distances, R1 and R2, equal, right? So the magnitudes are the same. So the up part of the one cancels out the down part of the other, and so the total force, or the total field, and the total forces are all just to the right. And so if you put a positive charge there next to a dipole, it would just get pushed straight that way. All right, wouldn't come towards or farther away, it would just go to the side, all right, towards the negative if it's a positive charge. If it's an electron, of course, it would go the opposite way. All right, hopefully you can follow that argument without having to do the calculations, or that might be a good homework problem or a test problem to do those calculations in detail. So do make sure you understand what I'm saying here. So finding the pieces, and again, these are the magnitudes. You could do the components with I and J, or and ratios, or if we got it in terms of angles, we could do sines and cosines, and calculate them that way. All right, we got a couple more minutes here. Let's talk a little bit about field lines. So say we had this dipole kind of idea. We have a plus charge, that's going to be a minus charge. I hope we can still see everything here. All right, we said electric field lines come out of positives, right? So they come out, and we want them to be, if it's a nice charge, to be uniform, and we try to draw the density of the lines, equal. Right, so if it's just nice uniform, there's equal spacing in between all the lines. They come out of positive, so these arrows would be going like this. And so individual forces are just little tiny arrows here, think of them as vectors, but then the field lines are just kind of lines that connect the dots. All right, so if we have a dipole, the field lines come out of the positive and go into the negative, and they will curve around and I unfortunately picked an even number, so let's pretend like they were too close to, anyway, they would come around and come in and split up evenly spaced. All right, so if we put, and this can kind of help us see the, my thing is not very nice and symmetrical, but it should be nice and symmetrical. Coming out and around. So if I put a charge in here, so the field lines are going this way. So if I dropped an electron, I'm carrying my electron around and I drop it right here, this is an electron, it's going to have a negative Q, right? And so some sort of negative E charge on my electron. And so what direction is it going to go? Well, electrons fight the flow, fight the field, so it's going to go this way. It's going to feel a force that way, and if it's allowed to move, it'll move that way, right? If I have a proton, put a proton here, which is a plus E, it's going to go with the field. So if we're not on one of the lines, but we can kind of, get the pattern, and it will have a force going that way, right? Because the field lines. And so if we're in a kind of a tight curve spot, we just make a straight line tangent to the curve, and that's the direction of the force, is the tangent to the curve. Okay? What if we had two pluses next to each other? Then what's going to happen? Well, so the field lines are going to come out, but they can't go to that one. They bend around each other, right? Because they can't cross. So they're going to be kind of nice and uniform out here where they're not being messed with by the other one. But then in here where they try to go straight out, they can't because they're the adding effects, right? Superposition, the field in here, just like we did the two negatives before. There's a place where it's 0, and then it's bending around. So lines closer together means it's a stronger field. Lines farther apart means it's a weaker field. So in here, where there's no spacing, because of the spacing, there's no line drawn. The 0 point is in there somewhere, right? So same kind of thing. If I put a positive charge in here, it's going to go with the lines, right? Or a positive charge here, it's going to go roughly that direction, right? Tangent to the lines. Negative Q, though, if I put a negative one in here, it would be pulled in the opposite direction, right? Okay, what if we had some sort of thing set up like this? We have a charge up here, and we have a conductor that's grounded. My ground symbol, drawn too many of them. Something like that. And so this is grounded, so it can draw electrons or pull in electrons or get rid of electrons however it wants to. This is a positive charge. And so the lines come out of this, and they'll actually be drawn down like so, because this will, positives are up here, it's going to draw negatives up from the ground, and they'll distribute out, and maybe more, anyway, however many charges. But it will make a nice symmetric picture and make the field lines all come down, something like that. So when we have a conductor, the electric field lines are always come in perpendicular, right? And so, because if we had electric field lines that were parallel here, everything is static, everything is sitting still. If the electric field line was sideways here, that would be making the charges move one way or another to the side, but they're static. Excuse me, they're static, so they're sitting still, so they can't have a component of force sideways, no sideways components at all, because that would cause them to move sideways, right? So the field has to, anyway, it's negative, so they're coming down. So they have to be straight down, perpendicular to the surface, all of them, at the surface, right? And so, similarly, if it was a positively charged, it would be perpendicular but going out. So let's just kind of try to draw one weird kind of conductor. So if this is a conductor, then if it's a positively charged, let's say it's got positive charges. Like we said in lab, they're going to distribute all around the charge as evenly, around the surface as evenly as they can, but now the electric fields are all pointing straight out, right, perpendicular to the surface. Even if it's a round surface, that just means normal or pointing straight out. We talked about normal vectors in Physics 1. This should be all kind of a continuous surface kind of idea. all pointing straight out. And the charges sit out on the top, right, on top of the surface. There is no inside the conductor. So one interesting property of conductors is that E is 0 inside a conductor. And this is kind of a similar argument. The charges are sitting still. They want to get far away from each other. Inside the conductor, they will flow out. But basically, that's kind of one of the laws of electrostatics, if you want to call it that, is that the electric field is 0 inside a conductor, right? Whenever you have a conductor, inside, E field is 0. All right, so it can be kind of this. Even if there's a whole bunch of charges, they will be pushed to the outside and they will stay on the outside of the conductor. So it doesn't matter if there's a whole bunch of positives, a whole bunch of negatives on the outside, inside, E is still 0. So remember that one. And again, the field always has to be perpendicular. Otherwise, the charges would be moving. And we're talking about statics here, the charges sitting still. All right? So what happens if we have something, a conductor, and there's a strong electric field outside of it coming from something else? All right? So we've got these field lines, and they will come to the conductor, but then there will be more field lines coming out the other side, right? Because minuses will line themselves up on the outside on this side, and pluses line up over here. So even if it was a neutral conductor, it can still have charges on the sides. And again, these are supposed to be perpendicular as they come out. On the sides, but if this is a sealed kind of thing, closed in, E is still going to be 0. The electric field will still be 0 inside of here. All right, so as long as this is a conductor, these are all for conductors, maybe it's some sort of a weird egg shape, right? The electrons can move around. There's going to be a field on the surface, or charges on the surface, and so the field lines can come to the surface, but inside it's 0. So this is like, they call it a Faraday cage, but it has a shielding effect, right? So if you want to get away from all the electric fields, shield your cell phone, your whatever. You probably don't want to shield your cell phone because the electric fields, the electric waves are what gets to your cell phone and gets you messages. But if you don't want any messages, go inside a nice conducting shell of some sort, and it will shield you from the fields. And so they will basically, the conducting electrons will, the conductor's electrons will situate themselves in so that the field continues around you, but inside it's 0. So this is used in lots of different applications where you do want to shield things from electromagnetic fields. You could, I imagine you've seen, if you're in a metal building of some sort, it's really hard to get phone signals. In general, it's hard to make a totally enclosed conductor, totally surrounded, airtight kind of thing, right, with no holes. But they make them as cages, and depending on the frequency of the fields, you can block out lots of fields. But you've probably seen when you're in a totally metal building, it's really hard to get phone signals in there because of the shielding effect. Alrighty. Let's go ahead and let's see, what do we need? We need some sort of an exit ticket, so we've gone back to the old-fashioned kind of exit ticket for today. And so let's go ahead and for the exit ticket, go back to this problem with the electric field right here, finding the electric field straight above the positive part of the dipole. And so we got this total electric field here. Calculate what is the force on a 1 microcoulomb charge. at that point, at 8 centimeters above, over the plus charge. Okay, so there's an exit ticket online, and use this information here and what we talked about in class today to calculate the force at this point, knowing that the electric field at that point is this value. Okay, so plus 1 microcoulomb charge at 8 centimeters above this end of the dipole. Okay, so we've got, it's one simple calculation, don't make it too difficult, and then turn that in on Campus Web for your exit ticket for today. And we'll go ahead and quit there.